Hello everyone, welcome back to Discrete Mathematics and its applications. Uh, Now we'll start our discussion on closures of relation. So let's get started. Um, so sometimes we are given a relation R that unfortunately does not satisfy some desired property. So for example, uh, not every pair of cities in Indonesia are connected by a direct flight. Yeah, these are very concrete examples. So not every pair of cities in Indonesia are connected by a direct flight, even when both cities possess an airport. So if there is no direct flight from two given cities, the question is, can the two cities be can the two cities be still be connected by a flight route? Well, not necessarily direct, but possibly with a layover. Well, the answer to this question can be obtained by computing the so-called transitive closure of the flight relation. So if you consider direct flight as a relation, then a flight route passing through a layover can be obtained by having the transitive closure of the flight relation. So this is an example where closures of relation are very useful. Now, in general, we could define a closure with respect to some property of relation. So for example, a property of relation is reflexive, symmetric, transitive, and so on. So let's say we have R, a binary relation on a set A. So that is R is a subset um, of of A times A. Now, and let P should be bold here. So this P, yeah. Let P be a property of a relation. Then we say a P closure of R, if it exists, is a binary relation S. So it's another relation. It's a binary relation S on A such that these three conditions are satisfied. First of all, the P closure of R, so S here, must satisfy the property P itself. So if P is reflexive, so you were talking about reflexive closure, then the reflexive closure of a relation must be reflexive. And then the relation R is contained in S, so it's a subset of S. That is, well, every relation is contained by its P closure. And finally, the third one, yeah, the P closure of R must be the smallest relation that satisfies both condition 1 and 2 above. So that is, if there is another binary relation R prime on A such that R prime satisfies P and R is contained by R prime, then it must be the case that the P closure is also contained by R prime. So the P closure is the smallest relation that satisfies the property P and contains the original R. Now, it is easy to see that P closure of R, if it exists, must be unique. To see this, why? Well, if you have two different P closure by condition 3, two different P closure, say S1 and S2, then by condition 3, S1 must be contained by S2, and well, S2 must be contained by S1. So this gives you S2. S1 is equal to S2. So P closure must be unique. So now let's have a look at least three closures that we are interested in. The first one, well, let me step back a little bit. So before that, the question is, how do we obtain a P closure from a given relation? Well, the idea is very simple. Actually, you could just do these steps, right? So start from R, and you check if R is, or if R already satisfies the property P. If so, then R itself is the P closure of R. Now, if this is the case, then we're done. Now, otherwise, we start with, say, R prime here by defining R prime to be R, and then we keep adding pairs x comma y from the Cartesian product of A times A to R prime. So you add pairs to R prime until R prime satisfies the property P. So essentially, you add pairs to R prime until it satisfies the property P. Now, of course, not every pair could be added, right? So the added pairs should bring R prime closer to satisfying P. So the idea is to add pairs to R prime so that eventually R prime satisfies the property P. Now, exactly which pairs must be added? Well, that depends on the property P itself. So let's start with the first example. The first P closure. This is when P is reflexive. So we're talking about reflexive closure. So suppose we have a binary relation R on A. Then the reflexive closure of R is the smallest reflexive binary relation R prime, such that R is contained by R prime. Yeah. So reflexive closure of a relation R is the smallest reflexive binary relation that contains R. Right. So that's the definition. So now let me give you an example. So suppose you have this relation R on A, where A is the set of integers 1, 2, 3, and 4. Now R itself is the set containing 1, 1, 1, 2, 2, 1, and 3, 2. What is the reflexive closure of R? Reflexive closure of R. Let me use this notation. Reflexive closure of R. Yeah. So this is, first of all, it must contain all pairs from R, right? So that means you add this. So you have this. Now, this is not yet reflexive, right? Now, you add more pairs to it so that eventually you get a reflexive relation. Now, because R is defined on A, where A contains these integers 1, 2, 3, and 4, therefore, in order to make this relation reflexive, then you add 2, 2, 3, 3, and 4, 4. So this is reflexive closure. Clearly, this is reflexive. Yeah, satisfying condition 1 in the previous definition. Also, we know that this is clearly that R is contained by its reflexive closure, right? This is condition 2. Now, is the reflexive closure of R the smallest one? Satisfying 1 and 2? The answer is yes, right? Because any other reflexive binary relation that contains R must contain other pairs other than this 1, 2, 3, 4, 5, 6, 7 pairs. Only these 7 pairs. If you add another reflexive binary relation, different one, must contain additional pairs, right? So this is the smallest one. Now let's do some exercise, right? So you're given two relations R1 and R2 there. So R1 is set of contains pairs of integers a comma b such that a is less than b, and R2 uh, contains pairs of integers such a comma b such that a is less than or equal to b. So give the reflexive closure of both. Yeah.